Hello, my name is Gonpat Prichakun. Today I'll walk you through our diffusion autoencoders. Our goal is to learn a latent code that has two key properties. First, the code should capture high-level semantics such as age, gender, and hairstyle of a given face image, for example. Second, the code should be fully decodable, meaning the reconstruction should look exactly like the input image. So two things, meaningful and decodable. Although vanilla autoencoders with a small bottleneck can capture high-level semantics, they tend to produce a blurry image because the code is too small to capture all the details. To improve reconstruction quality, recent techniques use a hierarchy of codes. However, these codes are spatial and lose the ability to capture global semantics like age or gender. Introducing diffusion autoencoders. To understand DFAE, let's consider diffusion implicit model, or DIM, that can generate a high-quality image from a noise map using a deterministic denoising process. One key implication is that we can run these backward and convert the image back to the noise map. Starting from an input image to the noise and back, it looks like an autoencoder already, with the noise map at its latent code. However, this latent code lacks meaningful semantics, which is a problem DFAE will address. Our key idea is to augment the whole diffusion process with a semantic code from a CNN encoder. Now, each and every diffusion step will be conditioned on the semantic code. The whole thing learns both to come up with a useful code and also to utilize it well for generating an image. So, DFAE can encode an input image to a compact semantic code and a stochastic noise map, which together allow near-perfect reconstruction. To see what I've really encoded in these codes, we did the following experiments. First, we encode this image, but we throw away the noise map and resample it from a normal distribution. The decoded image looks somewhat similar to the input overall, but it is no longer the same. We repeat this with multiple noise maps. With the semantic code fixed, the low-level changes like the hair pattern and wrinkles we observe here signify parts that are captured in the noise map. We also test whether the semantic code does indeed contain semantic attributes, like age or gender. If our semantic code contains gender information, we could train a linear classifier on only the semantic code to predict the gender well. And we could. We performed this test on the Celeb AHQ dataset. The results show that our semantic code is rich in semantics, with AURCs in 90s for many attributes, and higher than those from SciGAN W space. Note that we never used any labels to train the autoencoder. Training these classifiers also give us the weight vectors that correspond to the semantic change in the image. This allows us to easily do image manipulation in the semantic code space. We can add a weight vector V of a classifier predicting wavy hair on any semantic code to make the image look more wavy hair. Given real input images in the middle, we can manipulate different attributes such as gender, age, or hairstyle by simply adding or subtracting from their semantic codes. DFAE also allows smooth interpolation between any two real images simply by interpolating their semantic codes, thanks to the meaningful and linear semantic space. Another key benefit of DFAE is faster denoising. Here we show that what DFAE produces in 10 steps match what DDIM produces in 50 steps, measured in LPIPs. As an autoencoder, DFAE is not a generative model by default, because it needs a semantic code from the input. So to sample a semantic code without any input image, we learn another DDIM to sample from the latent distribution of the semantic codes. We can now sample a semantic code and a noise map to generate a novel image. Our method produces high-quality samples with comparable FIDs while requiring fewer steps compared to DAM across various datasets. To conclude, we proposed an autoencoder that renders good images with near-perfect reconstruction, a framework for learning compact semantic representation useful for downstream tasks, and a straightforward solution to many image applications which does not involve GAN and its error-prone inversion to operate on real images. Our code is online. Thank you for watching.